Any question? Are you ready? Nobody's there. Good afternoon. Are you there?
Yes.
Good. At least one brave person. Okay, let's start the lecture. Can you see my slide, please?
Yes, sir.
Good, sir. Now you are relaxed because I'm sure you submitted your report. And now you can sit down and pay attention to the lecture. We start chapter 8, as I mentioned last week. We finished for flow external force convection. We look at airflow over a flat plate, cylindrical coordinate, spherical, and we develop some correlation specifically for laminar case flow over the plate, but later on through experimental work, we were able to find some other correlation for other geometry. Now we are going focus to inside. If we have flow inside the pipe, that usually is either rectangular or triangle or circular. What we're trying to achieve in this chapter is trying to understand first how the flow is inside a system. Therefore, we're trying to define an average velocity from a knowledge of velocity profile. Therefore, we're trying to develop an analytical solution to look at the velocity profile, for example, inside the pipe. And then based on that one, we try to find the average velocity. I'm sure you understand what is the mean. The profile is a function of the R, but average we assume is a plug flow. Flow everywhere is the same. Then we use the visualization understanding of different flow regime in internal flow and calculated for hydrodynamic and thermal entry bundle. Therefore, we have two new terms here, hydrodynamic and thermal entry length. We're trying to understand what that means and how they will affect the answer. Then we try to look at analyze heating and cooling of fluid following a tube under constant surface temperature. Therefore, we have two types of boundary condition. In one case, we assume the temperature of for example, the tube remain constant. Another scenario, we assume there is a constant heat flux. Therefore, in case of hot constant heat flux, it doesn't mean the temperature is constant. The temperature changes linearly. Therefore, we're trying to look at this two scenario because these are the two common sort of application that we are dealing in reality. You have seen the definition of logarithmic mean temperature, but now we are trying to obtain that definition, that expression to see how it's work and applicable to which scenario. Is it constant temperature or constant heat flux, the trough? Therefore, we have to pay attention to this part because probably this is only applicable to one scenario. Then we try to obtain a sort of case of a Nusselt number for fully developed laminar. The same way we develop a model for flow over flat plate for case of laminar, because I mentioned in case of turbulent, the velocity is not well defined. But in laminar case, we know the profile of velocity. Therefore, we're trying to obtain an expression for Nusselt number in case of fully developed. Therefore, the velocity is fully developed is not changing as a function of the length. Then determine Nusselt number for fully developed turbulent flow by empirical. Look at here, this is we are trying to develop analytical technique, but here again through the sort of experimental work, we're empirical technique to try to find a way to define Nusselt number for turbulent flow. Therefore, these are, we hope we have some understanding when we finish this chapter. Again, this is, we have to pay attention to different topic that we are going to discuss, and this one by one we are going to discuss it through the presentation. Look at here, we have pipe, we're dealing with flow inside the pipe. We have a rectangular duct that we usually have an air conditioning system. We have a flow inside going duct, okay? Through duct pipe is commonly used in building heating and cooling application. We have a pipe, for example, for water pipe, we have air through to all mechanical ventilation system that we have in the building. In such application of force, in order to bring the fresh air to your room, to the mechanical system, we have a fan. That fan pushes the air. And air passing, the water passing, going through the boiler or chiller and so on, we are pushing a fan, we're using a fan, a pump to push it through the pipe. Therefore, we have, that's why we call it force convection. There's external force pushing the fluid past through the system. Street is the same. Although the theory of fluid flow is reasonably well understood, theoretical solutions are obtained only for a simple case. Okay, that's why for laminar flow we use, because it is a sort of well defined. We are able to find the velocity profile, and from the velocity profile find the temperature profile. Therefore, even though we have the rule conservation of mass, conservation of momentum, conservation of energy, but only in very simple case, we can develop a sort of analytical solution for that problem. Therefore, in case that we cannot, we go back experimental. As I mentioned, experimental, we carried out experiment in the lab. We're trying to find the relationship between the parameter, and then we plot them in sort of, as for example, Nusselt number as a function of Reynolds number, trying to define the heat transfer coefficient. Okay, this is that we are, at least we are aware of so far. If you look at here, the velocity profile, we know that this is following this pattern. And we mentioned in case of, through your fluid mechanics course that you took, you were able to find this velocity profile, okay? We know at the center, at the border and the pipe surface, because of non-slip condition, the velocity is 0. As we move from the surface to the center, the velocity slowly increase, and velocity at the center is maximum. As I mentioned in the chapter 7, assume this one is only one side, the velocity profile continuously, but we have an upper boundary condition like a pipe, the velocity here is also developed, and at the center, they try to balance each other. That's why the velocity profile is symmetric. Therefore, symmetric at the center is maximum. When we define all of those variables that we need to calculate, for example, Reynolds number, the velocity equation Reynolds number is average velocity. Therefore, we assume the whole velocity is uniform, is not a function of r. Therefore, this is the average velocity, and simply we can calculate by integrating velocity profile and divide it by surface area. Therefore, this is when we discuss average velocity, it means everywhere is the same, okay? And this is the term, the value that we are going to use when trying to calculate Reynolds number. Therefore, this is examination. Fluid velocity in the pipe changes from 0, as I mentioned, because of non-slip condition, all the way to the center. In the fluid flow, it is convenient to work with average because this is easy. You can obtain it experimentally. Just put an opening here, take the water, and then put it in for a certain time. I mentioned this my velocity, average velocity. Okay. In practice, we calculate the fluid property at average temperature. Again, when we're trying to calculate the Nusselt number, again, is the question the temperature. We have the temperature variation. Therefore, the temperature varied, but we also define an average temperature. Therefore, also all the physical property will be calculated at average temperature. When we look in here, if you have here flow inside the pipe, a square duct, rectangular, all of them, and sometimes we have in case of channel that we have the probably is not completely full, therefore probably half. Therefore, in all of cases, when we're trying to calculate the Reynolds number, the characteristic length, we have to define the characteristic length. In the case of pipe, we define D. That was the diameter of the pipe. Therefore, we're trying to also define a term that has the same representation as the diameter of the duct. And usually, this is the case we have. In Reynolds number, we mentioned average velocity, not the maximum velocity, not the minimum velocity, the average velocity. And that's the case. We can easily change it to mass flow rate, okay? By multiplying up and down with the PD, we can get mass, and therefore you can also use either this equation in some problem, rather than they give you the velocity, they give you the mass flow rate, okay? Therefore you can use this equation to calculate the Reynolds number, okay? But also in case of that we have a square duct. Yes, sir.
For the mass flow rate, we're gonna need the row of the fluid going through.
Yeah, we have the row.
Are we considering T median, or the T we consider it constant throughout the whole thing?
As you know, the conservation of the mass is when we look at the mass, therefore is irrelevant of the concentration because we are measuring the mass, kilogram that side. Okay, therefore. In that case, you have already the value of the mass is given to you right here. Okay. Therefore, here you have the Nusselt number. You multiply top and bottom with the mass flow rate. Here is the mass flow rate, and this is the.
So it doesn't matter if we take the density at the beginning or at the end of the duct system.
This is the mass. Is the value is given to you in the problem.
Oh, okay.
The value is given to you. Okay.
Right.
But that's the value given to you, therefore you are not worried about it. But yes, you are right. When it comes to the viscosity, therefore we have to calculate the viscosity at what temperature? At bulk temperature. Okay?
Okay.
Again, we're going back, and later on, when we the same thing we did it for flow over a flat plate, each correlation, they specify a certain temperature, sometimes the bulk temperature, sometimes the average temperature, inlet and outlet, and so on. We get to that part. Good question, sir. In case of when we come to discuss about the square duct here, therefore we have to define a sort of an equivalent diameter, because we are here, equation give it a characteristic length. Therefore, with the way we define, we call it hydraulic diameter. Hydraulic diameter. Therefore, this term, again, remember what that means, is it means it's if we have a duct like this, what would be the equivalent in the circle? Therefore, this is the definition. The cross-section area divided by perimeter, okay? Therefore, in this case, we can define for any of those cases, what is the perimeter here, this, plus this, plus this, plus this, times 4 times surface area, okay? Therefore, this is the cross-section area, A times A times B, and B times E, okay? Therefore, that's for example in the case of a tube. This is the definition 4 times this one. Therefore, this is the cross-section area that you have here divided by the perimeter. Therefore, in case of tube is the okay. The same thing we define for square, for hydraulic, rectangular, and so on. Therefore, keep in mind, depending on the geometry that you have to use again appropriate characteristic length. That's very important, which we remember. Therefore, this is now we call it DH in general term, and DH it means this term right here. Again, we're going back to the pipe, and going back to a fluid mechanic, again, now here is your critical Reynolds number is 2,300, okay? It's laminar if it's less than 2,300, okay? And this is more than 10,000 become turbulent. Therefore, now remember, keeping track of the geometry that you're dealing, keep is it circular, is it external or internal? These are different critical Reynolds number that you have to keep track of. You have seen this one in fluid mechanic. Remember, again, we assume the condition that, again, the velocity entered the pipe, this is uniform velocity, okay? This is the average velocity entered the pipe. And again, because of the condition that we have, non-slip condition, the velocity on the surface is 0, and then we have the viscosity phenomenon slowly change until reach the maximum here, and the same thing with therefore here at the center we have the maximum velocity. Now, remember we have the term, we call it develop and developing. Therefore, from here, the velocity profile will not change anymore. The velocity profile remain the same, okay? But from entrance right here to this point, we call it developing velocity, okay? Therefore, the velocity profile here is flat, uniform, slowly developing until you get to this one. Therefore, this is, we call it entrance region that we have here, okay? And therefore, here is called developing velocity profile, okay? Developing velocity profile, it means it still is not fully developed. After this point, after this line here, it's become fully developed. Therefore, this is, we call it a fully developed region, and here is hydraulically, slowly the velocity profile is developing. Therefore, keep in mind what that means. Well, the average velocity in all the cases is the same. Average velocity is the same, but velocity profile is changing. Now, pay attention to this terminology, at least to help you to be able to understand the physics of the problem. We mentioned velocity boundary layer, the region of the velocity in which the effect of the viscosity shearing force caused by the fluid viscosity. Therefore, in this region from here to here, the velocity profile is slowly influencing the viscosity, okay? Therefore, this is the part that we have to remember. Boundary layer region, the viscosity effect and the velocity change are significant, okay? In that region that we had in before, in this region, the velocity is very affected by viscosity of the fluid. A rotational fluid flow is in the sense that we discussed here, at the center is not influenced by the viscosity. For this region, we call it rotational flow, okay? Hydrodynamic entrance region, the region from the pipe inlet, x equals 0, to the point at which the velocity is fully developed. X0 to this one. This is called hydrodynamic entrance region. From x0 all the way to this region. Okay, that's what. This L, this is the length of that section. Okay, you can calculate how long it takes the velocity to become fully developed. There is again the same thing that we had for flow over flat plate. Now we have it for this scenario. That's again, it's a function of the Reynolds number. Hydrodynamically fully developed region. Okay, that's fully developed region. The region beyond, from here, from this point here, the entrance region that reach the velocity is fully developed and remain constant. Okay, therefore this velocity profile will not change. From here to here, the velocity profile keep changing. Okay, so we look at here, but after here will not change anymore. Okay. Please read this one, keep trying to understand. Flow in the entrance region is called hydrodynamically developing. Therefore, here is developed, here this part is developing region, okay? That's trying to familiarize yourself because, again, we have to understand when we're trying to use a correlation, is it developed for fully developed region or for the entrance region, okay? Okay. Therefore, we have to keep in mind because these are the mentioned here. When it's fully developed, probably we have to use one set of correlation for Nusselt number and another one for this part. Because here the velocity is not fully developed. From here, the velocity is fully developed. Another Nusselt number. That means another heat transfer coefficient. Any question, ladies and gentlemen? Okay. Now the entrance region we mentioned here is, please keep in mind here again, we are talking about Reynolds number. Reynolds number is changing, therefore we have to keep in mind what condition is the system is exposed to. Constant temperature, fully constant heat flux, and so on. In the internal flow, we usually evaluate at the bulk mean temperature. Bulk mean fluid temperature. What that means? The fluid enter here at Ti and leave at Te. Okay. Therefore, we have to find out what that exactly means. It means the average temperature at the inlet and average temperature at outlet divided by 2. Because if, for example, if fluid comes at 10 degrees and exposed to a surface 80 degrees or 90 degrees, the fluid is entering the pipe probably 60 degrees. Therefore, there is 50 degrees difference for entrance and at that point. Therefore, all the physical property we're trying to calculate is that we call it the bulk temperature. The bulk temperature, it means the average of inlet and outlet. This is I and inlet, E exit. Thermal entrance region is the region of the flow for which the boundary layer developed, and that we discussed at that before. Again, entry layer we mentioned here. We mentioned what is fully developed and developing. These are we have to make sure that we really understand this definition. Okay. Therefore, the reason we are emphasizing here is the correlation that we are using are different from entrance region and so on. We had it for the velocity before, and this is for the thermal. The same condition we discussed about the velocity development, this is also with the temperature profile. Therefore, with the same, we have thermal entrance region, thermal entry length, thermally developed flow, and fully developed width. Therefore, we have the same discussion for the velocity also apply here. Again, fully developed flow, the region in which both velocity and temperature is developed. Keep in mind, when we're talking about the temperature profile is a region that when we use this term, for temperature thermal, it means the temperature profile has been fully developed, and also for the velocity. Therefore, keep in mind what we discussed before. This was for the velocity, and here we are talking about the temperature. Okay, the same exactly terminology. Now, if you look at the flow inside the pipe, for example, in this case, we assume the velocity profile, the temperature profile is here. This is the yellow one, and the blue one is velocity. Therefore, the velocity profile is developed first, then the temperature profile here. And if you look at the heat transfer coefficient, the same thing applies to friction factor, but let's focus on heat transfer. If you look at this along the length, this is the length of the pipe. This shows the effect of the entrance phenomenon. Until this part, okay, until this part, the fluid is not fully developed. After this one is fully developed. As I mentioned, because of the Prandtl number that we saw before, and we will see it again, the velocity profile will develop faster, and then the temperature. Again, that's depend on the Prandtl number. If the Prandtl number is equal to 1, the velocity profile and the temperature profile will develop at the same time. For example, in this picture, as we have here, the figure we have, it shows the velocity profile is fully developed first, and then the temperature profile. If we are dealing with a liquid metal, like a mercury, in that case, the temperature profile will develop first, okay? And the whole idea it's trying to say here is even the laminar or turbine, the heat transfer coefficient at entrance is infinite almost, slowly decrease, and when we become fully developed, remain constant. It means from here all the way to the end, the heat transfer coefficient will not change, okay? That's the meaning of it. Let me go term by term. Hydrodynamically fully developed. In this case, when we assume here, it means right here, velocity profile at this length here. After this length here, the velocity, it represents only as a function of r, is not a function of x. Therefore, when you're using this term, mathematically, it means this. variation of the velocity with respect to x is equal to 0. The velocity is still a function of r, but it's not a function of x. Therefore, when you mention hydrodynamically fully developed, it means your velocity is not function of x, and that's exactly right here. It's fully developed, it remains constant, okay? That's the mathematical meaning. Therefore, when you use this term, automatically, mathematically, it means this, okay? When we've mentioned thermally fully developed, unfortunately, we don't have a mathematic here, but we're using this term, that the temperature variation here, again, is similar to this, the temperature is a function x and r, temperature x and r, okay? Again, the same, it means after that, the temperature remain constant, okay? The temperature profile remains constant, okay? But usually what we do here, we use this term to define the velocity is fully developed, is not a function of x, and temperature is not a function of x, again, the same. And therefore, when it's not a function of x, that's why we use this equation for Newton cooling law to calculate the conduction. This is equal to this. Therefore, the temperature is only a function of r, is not a function of x anymore. That's the expression that we are using. That's the only time we can use this one. That's entrance effect is gone from here. Before that, I cannot use any of this equation. Therefore, from here, when I find the temperature profile, I can define my x. Please interrupt me whenever you have a question. Okay. Again, look at here, please. Read, this is exactly what we're trying to say here. In thermally fully developed region of a tube, the local convective heat transfer is constant, is not a function of x, because the velocity profile and temperature profile remain constant, therefore the heat transfer coefficient remain constant. Okay, read this one again, please try and relate it to what we said before. I forget about convection, the friction convection heat transfer remain constant in fully developed region of a tube. Therefore, here, contrary to the case that we have for the flow over plate, it's not anymore function length. Here is the boundary layer remain constant, the heat transfer remain constant. That's exactly what we're trying to say. The same thing because of the friction factor, pressure drop at entrance is more than that. Okay. Any question? Now, based on the study had been done, we look at here, we can see here, it shows x over dx is length, d over diameter, therefore they use non-dimensional here. And here it shows Nusselt number. Look at here, it mentioned Nusselt number xt. Nusselt number xt, it means it is the constant temperature. Therefore, in this case, we assume that temperature of the surface is constant, okay? And here, NuH, it means constant heat flux. Therefore, again, two different scenarios. In one case, we assume the surface of the pipe is constant all the way. The other one we assume is a constant heat flux, okay? Therefore, again, trying to understand physically when such a thing will happen. Okay, the entry length for both cases, look at here, the entry length here is for laminar is 0.05 times Reynolds number times this. You mentioned this is that after this length, the velocity is fully developed, okay? This is the entrance length, okay? The entrance length is this one. This is therefore approximately, they mentioned this number, it becomes Reynolds number and D. After this length, the velocity is fully. Therefore, you can always verify this case for any problem that you do, if it is fully developed or not. You calculate Reynolds number, and from this equation, perform. The same thing we have for turbulent, okay? Okay. This is, I'm sorry, for the case of the thermal, okay? For the entrance length, for laminar, both of them laminar, in this case, we have constant heat flux. In this case, we have constant temperature. Two different boundary conditions. In this case, is a function of the Prandtl number, you can see here. In general, we can use this term. Mentioned is almost, in case of turbulent, is almost 10 diameter. Okay, this is laminar and experimental that did it for for turbine is almost 10 times the D. It's very important for you to know that, because when you start to investigate a building a measurement that you're doing, you have to measure the velocity inside the duct, okay? Therefore, you have to do the measurement 10 times after the diameter. After that is turbulent. It means the velocity almost, you can assume, is identical, okay? It's almost flat, almost, not exactly, okay? When it comes to Nusselt number and H value are much higher in the end transition. If you look at here, this is Nusselt number indirectly represent heat transfer coefficient. Again, this is Nusselt number indirectly represent. If you look at that line, it constant heat flux. The green line represent temperature. If you look at in all the cases, the heat transfer coefficient for constant heat flux is a little bit higher than constant temperature at the end transition. After that, if you look at 10 diameter of this one here, right here, after here, this one right here, it remains the same, okay? The Nusselt number reach a constant value at the end. Yes, sir.
What is X? Is it
X is the length of the pipe. X
okay.
The length of the pipe.
Any type.
Length of the pipe, any type, because here D is the H. D is the H. Therefore, is hydraulic diameter.
That's only for circular pipes.
This is the pipe. You can apply
only applies for circular pipes, nothing else.
It's again, if you are using DH, apply for any case. Assume here the type of dynamic is DH. Okay. Did I answer your question, sir?
Yes.
Okay. The Nusselt number is a constant value, as you can see from this graph. After 10D, look at here, we are talking, these are, all of them are more than laminar, therefore all of them turbulent. For turbulent case that you have, after 10D, this is the 10D that you have, you can reach almost constant value. Okay, you can bring it here. Okay, therefore it remain constant. And the Nusselt number for uniform surface temperature and uniform surface flux condition are identical in the fully developed region. Okay. Therefore, after when it's fully developed, the heat transfer coefficient, as you can see, for constant heat flux and constant temperature is almost identical after that. And before that is almost the same, but after that is all the same. Okay. You can see after 10 diameter here is the same, okay? Now, we're trying to find now the way to somehow to solve the problem, okay? Therefore, we learn a little bit basic. We learn about a certain terminology that we are going to use those terminology directly or indirectly in solving the problem, okay? Now, let's look at different scenario that we have, okay? Let's look at the thermal condition at the surface can be approximated to this one, okay? Let's assume that you can assume the surface temperature of the pipe is constant, okay? The surface temperature is constant here, okay? The fluid enters the pipe at a given temperature of Ti, inlet, and leave at Te. Okay, there is a certain amount of energy we transfer, but this is not constant, but the temperature is constant. Okay, therefore we mentioned constant surface temperature. We can calculate the rate of heat transfer simply applying this equation. If we know what is the inlet temperature, what is the outlet temperature, I know the mass flow rate. Again, this is mass flow rate, kilogram per second, and so on. Therefore, I can apply this equation and try to calculate this part, okay? But there is another case that we assume is constant heat flux. Therefore, I'm providing a certain amount of the energy to the wall, but doesn't mean the temperature is constant. Please keep in mind, a constant heat flux does not mean the temperature is constant. The temperature change along the pipe, okay? In this case, we can mention this is the amount of the heat flux. This is known value. Therefore, here is the temperature of the surface, and this is the mean temperature of the fluid that we defined before, okay? Because here I do not know exactly what that means, but this is the mean temperature coming TI here and TE. We are trying to define this one later on, okay? Because this is TS is the temperature of the surface, and here is the temperature of the inlet and outlet. Because this, we are using the mass flow rate, okay? Please stop me whenever you need some question. Again, trying to understand the problem when you're trying to solve the problem. The constant temperature condition is idealized when there is a phase change process, such as boiling. When there is a phase change, what that means is it's going through liquid to vapor. The temperature is constant. Or condensation is coming what from vapor to liquid. The temperature is constant. In that case, we can assume the surface temperature is constant, okay? When dealing with constant heat flux, it means we are providing a uniform heat flux. For example, you're wrapping a heater around your pipe and providing electricity. In that case, the heat transfer everywhere around the pipe is the same, okay? Therefore, try to understand the physics of the problem related to the math of the problem. Now look at what the constant heat flux, okay? When you have a constant heat flux, as I mentioned, you're providing a constant flux. Everywhere is the same, okay? Therefore, as the fluid, the temperature will increase, the temperature of the surface also will increase, okay? This is the fluid temperature. It comes inlet here and leaves our outlet here. And this is the temperature of the surface at the beginning, a little bit cold, and slowly increase and go on. After the entrance part, after this part here, look at here. These two temperatures will increase almost the same rate. What that means, the same rate. Again, this is very important for us to learn. It means the slope of this line, and the slope of this line is almost the same. Look at here, this one is parallel. Temperature of the surface, the bulk temperature of the fluid, both of them increasing almost linearly, okay? This is only applicable to constant heat flux. If I look at here, the rate of heat transfer, I can write it down because I know the temperature coming in. If I can calculate the temperature out, I know the mass flow rate inside the pipe. I can calculate how much it is. And this can be done easily because I know the heat flux. I know how much heat provided, depending again on the problem. Therefore, you can see either I know this one or I know this one. I can calculate the problem. What is again velocity? Here is TE and TI. We can calculate TI as simply from this equation because I know how much energy I provided from this expression here. Therefore, I can calculate T exit from this expression here is TI minus this. And surface temperature, I can calculate surface temperature from writing an energy balance equation. Okay, I can do that one easily, and I can calculate that part. Okay. Look at the equation. If you have any question, please do ask. Look at the equation to see if you have any question. This is simply as energy balance we wrote for the mass flow rate here that you have. And here it's simple energy balance by convective transfer. Okay, right here. From here, we can calculate the exit temperature. And from here, we can calculate surface temperature. Yes, sir.
Could you please go back to the previous slide? I wasn't done writing.
Okay, let me go back. Ask me if I go fast. Please let me know because I'm not there. I don't see your face. Therefore, yes, sir.
Thank you, sir.
Please let me know whenever I go fast, okay? Your camera is off. I do not know if you're sleeping or you're watching Netflix or you're listening to me. Therefore, please let me know if I go fast. Therefore, in the case of, again, remember constant surface heat flux, okay? This is, please remember this solution is that case, okay? Therefore, I can calculate the mean exit temperature. Again, these are mean exit temperature, and here is mean surface temperature. Okay, we look at here, as I mentioned, in this case, the temperature goes up, the surface temperature goes up. Okay. Any question? Let me go to the case that we have here. If I wrote a simple energy balance here, if I take a control volume and I write all the energy involved, some energy goes by the fluid, therefore here, right here, and there is some heat flux is coming here. Therefore I can write mCp delta T. This is the change variation of the temperature from this point to this point. dT has been increased from here to here, and here how much energy comes through that surface area. Therefore a simple energy balance for this control volume. And this value is constant. It's constant. The simple reason because my heat flux, I'm trying to justify why this is going like this, okay? Therefore, I can see here, this is my Q, heat flux is constant, M constant, P constant, therefore this value is constant. Therefore, you can see the variation of the fluid temperature is constant. The same thing we can mention about the surface area. Okay, therefore this is the justification why we mentioned the variation of the temperature of the fluid is the same as the temperature of the surface, and that variation is constant. And that simply can be calculated from here. We know how much heat flux we provide, how much is the surface area of the perimeter of the pipe, and here. Therefore, that indicates that this, what we mentioned earlier, is the slope of this line is exactly the slope of this line. Therefore, we can calculate easily the variation of the temperature. Okay, that was the justification that we mentioned. The same thing that we can use for circle tube. Okay. Any question, ladies and gentlemen? Therefore, now we realize the variation of the temperature of the fluid, the same as the variation of the surface temperature in case of constant heat flux. Okay. If you would like to visualize what that means, it means there is this velocity profile is not changing. The velocity profile from here, now it's fully developed, is the same, is independent of the x. Velocity temperature profile is function of r, but it's not a function of x. Okay, it means this profile is exactly the same profile after it's become fully developed. Okay. Okay, let me go to next slide. Now we're talking about constant surface temperature. As I mentioned, we have two boundary conditions. One boundary condition that constant heat flux, but the other condition, the temperature of the pipe along the pipe is the same. The temperature is the same, but the Q are different. Therefore, rate of heat transfer to or from the fluid is in the tube. It can be calculated by here. We know the surface temperature. If I know the value H, therefore I know the average temperature of the fluid. Again, what is Tm? That's the part here is a little bit confusing. We know the Ts because we mentioned it's constant. What is exactly mean temperature of the fluid? A function of the length of the pipe. Okay. Therefore, we can have two scenarios. I can easily mention, look at here. The Tm is the average temperature of inlet and outlet. Or I can develop a more accurate way. I'm sure you're familiar with this terminology, called it logarithmic mean temperature. Okay. Therefore, when I said arithmetic, it means simply Look at here in this scenario. The temperature of the surface of the pipe is constant along the pipe. From here all the way, the temperature remains constant. Again, I told you the case that we can assume we have a tube and there is some boiling water pour on the surface. Therefore, we can assume the temperature everywhere is 100 degrees. Or we assume there is vapor is coming here and start to condense. Therefore, the temperature is 0. Therefore, the temperature everywhere along the pipe, again, we're talking outside, is constant. But when I'm going to look at inside the pipe, the fluid comes, for example, at, in this case, is heating, the temperature is coming at Ti, and as move along the pipe, the temperature slowly increase. And after long distance, the temperature become here. Look at here, the temperature difference between T of the fluid and temperature Ts is that big. When it exiting here, that become that the temperature difference is small. Therefore, I cannot mention the Tm in this expression here is the average of this plus this. This is not accurate because the temperature difference just keep decreasing. And if you look at exponentially here, okay, look at the temperature here is exponentially is increasing. Therefore, we have to be able to find out a way to define this temperature difference, what exactly this temperature difference means, okay? That's the focus of our topic right now. Therefore, when I'm trying to apply here, I mentioned H equal A delta T average, what that means average, what that means, how can I define this temperature? Because the delta T is keep changing, okay? From here all the way to here and all the way to here. Again, we can start looking at this scenario that we have a pipe, the fluid is passing through it at the temperature of Ti, my inlet temperature, exit at Te, and the temperature along the pipe everywhere, the surface temperature is constant. If I take a control volume, the control volume of the fluid, again, based on average velocity that we have here, average temperature of the fluid in our direction, I know that fluid is coming with the Tm and leaves with the temperature this plus this. Therefore, this is a change in the temperature. And here the surface temperature is constant. Therefore, I can calculate how much heat transfer coming here, okay? Assuming that I know H, but at this point, okay? Therefore, I write a simple energy balance equation. Variation from here to here is become this. And this is the amount of the heat transfer from that surface area. This is a Ts, and this is the bulk temperature Tm. Therefore, I can simplify here again the dA. What that means is the surface area that we have times the delta x. Therefore, this is the perimeter that we have of the pipe PD times dx. This is the surface. Again, you can see that this is we are circular here we're talking. And I replace them here also. I can find this expression right here. The dTm that here, again, Ts is constant, it doesn't matter. Therefore, this is again representing the same term that I have here. This is Ts minus this one. This is H right here, and that's here. Therefore, this I can write. The reason I put minus here, because I put a minus here. If I take the derivative of this term is 0, and this term become minus dt. And that exactly we had it over there, okay? Therefore, minus become plus, okay? Therefore, we have this expression. Any question about this expression, please? Do you have any question how we get this far? Therefore, we write a simple energy balance equation for a control volume, and we replace them by the variable that we have. Again, we are changing the temperature because we have here dTm, and here with Tsm. Therefore, this is exactly the same as this one we had over there, okay? Therefore, the derivative of this one is exactly the same as the derivative of this one. Now I have a differential equation, first order that I have here. Therefore, I need one boundary condition, and we can mention that at x equals 0, the temperature of the fluid is equal to Ti, okay? Therefore, we change this one, and we end up with this equation. I'm sure you remember this equation we used last lecture. Therefore, I have now an expression that tell me the relationship between temperature inlet, outlet, and surface temperature. Okay, And that's exactly the equation that we have. Therefore, this one equation that we used last lecture to find the exit temperature, okay? And that's exactly the case that for constant surface temperature. And I can write this expression as function. This is log m, this is E, therefore this is the same as the equation over there that we have here. Therefore, I have an expression now to calculate the exit temperature. Any question, please?
Excuse me, sir.
Yes, sir.
What if they ask for the temperature like in midway?
Oh, I will do that one. Let's go step by step. Okay. You are at this point, at any point, right? At any point, you mean, right?
Yeah, yeah.
Therefore, this x that we have right there, when we calculate here, we mentioned that if this point at x equal L is that value. Therefore, we can identify where is my L. I can calculate that temperature. Okay.
Okay, so just the boundary conditions change.
Absolutely, absolutely.
Okay.
Okay. Therefore, this could be temperature at any point. Okay. Do you know why? Do you know why?
Do I know why? What?
Do you know why that this temperature could be any place? Because this is the surface area, and this surface area is perimeter times length, right here. Okay. Therefore, this is the perimeter of the pipe, pi d times x. Therefore, when I calculate this S here, it means PD times L. That L could be X. Therefore, that temperature could be at any point. Okay. This is
yes.
PD times X. Okay. If I want at the end, this becomes PDL. Okay.
Okay, yes, thank you.
Okay, no problem. Now, for internal for convection, as I mentioned, the question here is, we mentioned right here, H. If I know H, all of my problem will be solved, okay? Because I can calculate the surface, the exit temperature, and so on. But now the question here is, what is the value of H for internal flow? We have already some idea about external flow for cylinder, a sphere, plate. But now what is inside? The fluid now is moving inside the pipe. And the question is how I'm going to evaluate, okay? Therefore, at the end, I have to use this equation here. I have to find the value for H. What value should I use for H? The focus now here is we're trying to find a set of procedure or set of equation to calculate the heat transfer coefficient, okay? Now, how can I calculate the heat transfer coefficient? Look at here. You remember this one, the velocity boundary layer, okay? The velocity profile, okay? This is the pipe, the fluid is passing to it. I take a control volume. Again, this is a cylinder, small cylinder. The thickness of the dx, and we have, again, is a control volume. This is radius r, and this is r plus dr, okay? And if this my control here, I have under sort of like, if I write a momentum balance, there's a pressure comes here, a pressure goes from here. There is a shear in this direction, there's shear in this direction. Therefore, if I put a value here, this becomes like this. The surface area times this is the pressure changing. Again, here is shear, and this is the area dealing with it. Therefore, I can write a simple force balance equation, and I can find the relationship between the pressure and tau. Therefore, keep in mind this simply write based on the force balance equation. Okay, a force balance, I write all the force acting on this control volume. I can end up with this expression: dp over dx is equal to tau. This is shear divided by r. Okay, let's go one step further. This was we did right here. And this is exactly what happened. And from here, we were able to find this expression, okay? Therefore, that's, we wrote a simple balance here, right here. This is pressure on direction R that we have right here. Look at here, this is RdR right here. This one at delta X plus delta X. This is shear and so on. We simplify, and we know shear stress, the definition, and we assume it's Newtonian. Therefore, we can apply this tau is equal minus mu. And from this one also we find another expression by replacing tau here as a function, tau here as a function of right here as a function of the velocity. Therefore, this expression that we find here. Therefore, we take this expression by simple force balance, we replace this one. Therefore, now I have an expression that gives me velocity as a function of R and pressure. Okay. Remember, before we mentioned after entrance length, pressure does not change. Pressure change, but it's not a function of x. It means the variation remain constant. When I mentioned dp over dx is constant, pressure change, but variation is constant. Therefore, we can assume this value is constant, okay? And this the same thing, I believe you make the assumption in fluid mechanics. Pressure change. As I go along the pipe, the pressure change. But what I'm saying is dp over dx remain constant. The rate of change remain constant. If from here to here, the variation was 5, from here to here is 5, from here to here is 5. That's the meaning of that one. Now I have this differential equation. I can start to solve it. I need two boundary conditions. I know the velocity at the center is the maximum. I know the velocity at the wall is equal to 0. Therefore, I can solve. I can find this expression. Okay. Therefore, I can find here. C1 and C2, I mentioned at the center velocity is maximum. It means the variation is 0. Again, this is symmetric. I hope by now you understand what that means here. The velocity is maximum. That means there is no variation at this point. This is the maximum. Maximum, it means the first derivative is equal to 0. Okay, that's the meaning here. Okay, therefore here at the R, this velocity is 0 because non-slip condition. If I replace in this expression, and I get this expression. Again, I mentioned here is dp over dx is constant. This is very important to remember, okay? Therefore, this value is constant. Now I can calculate the velocity profile anyway, at any point in the R direction. And I'm sure you remember that this is, you can integrate it from 0 to R, and by putting velocity and so on, you can find an expression for velocity. And this is, remember, this is velocity profile, the average velocity at any point. Therefore, I can here calculate the velocity at any point, or I can calculate the maximum velocity. Any question? This set of equations, I believe we went to it quickly in building science, and you have seen it in fluid mechanics. If you have any question, please ask me. This is the last time you are going to see it for the rest of your life. Any question? Okay. Therefore, now I have an expression that I can use to calculate the velocity profile. Okay, I can use and calculate the velocity at any point in the R direction. Now, I'm trying also the same thing we did for flow over flat plate. I'm trying to find the temperature profile. Okay, therefore I have the velocity profile. I write now a simple energy balance equation. A simple energy balance equation. Again, I take the control volume. Some energy goes by the fluid motion, advection, and also we have some conduction this term. Okay. Therefore, this is control volume was selected. This is cylindrical. Okay. Therefore, we can try to calculate it down. Some energy moves advection by fluid motion coming in at x and leaving at x plus delta x. Some conduction coming here and some conduction leaving here, conduction coming leaving here, right here. Therefore, I can define mass of this fluid going here easily by knowing the velocity profile. Because this again average velocity, we can this is the velocity as function of R here, right here, because it is a thickness. Therefore, by putting together these two equations, I can simplify this equation. This represents energy by fluid motion. This term represents energy by conduction. Okay, by conduction. Okay, this is constant, this is conduction. Okay, therefore, this is very important to start to understand each term. Okay, therefore, now by replacing Q that we have as a function of Fourier equation, Q is equal to dt over dtr by here. This is exactly the case that you have. This is the area of this cross-section area of this control volume times dt over dr, and therefore this becomes this term that we have, because you remember this, we have r, because r is still is variable, we cannot take it out. Therefore this term again remain here. Therefore this term represent again by conduction in the r direction, and this term represent both fluid motion. If you look at here, I have one equation but two variable, temperature and velocity. But we already have an expression that give us the u as a function of r, okay? Therefore, we can replace by expression that we obtained earlier, because this is now we can replace it by a function of r, and we try to solve this differential equation that we have, okay? And again, it's a second order right here, but we have two boundary condition, okay? Therefore, we can have to that. Therefore, please, again, is not equation trying to understand the physical meaning. We mentioned the rate of net energy transfer to the control volume by mass flow. This represents mass flow. This represents by mass flow is equal to net heat conduction in the radial direction. Therefore, how much go in this direction is the same as going around this direction, conduction, okay? Now, therefore, we are trying to find the temperature profile in this control volume, okay? Again, assume it's replacing here. Again, this equation does come right from this expression that we had before. Therefore, now the TTM, we mentioned before, we obtained that this one is constant. Let me see if I mess up with my expression that we have here. Look at here, the case we mentioned this is change. This was constant before, but now we are coming this case, and we mentioned this Q that we solved from this expression right here, that we're trying to replace this one right here. Let me just go back again. And we end up at finding a temperature profile. We have an expression, if I know this value, I can calculate the temperature at any point as a function of R, okay? I can calculate the temperature profile. I need two variables, C1 and C2. I need two boundary conditions. We mentioned at the center of the pipe is a maximum temperature or minimum temperature. Therefore, this is dET over dx equals 0. When it comes to the mention, and also, therefore, I can calculate this one, find this expression. This expression give me the value for TS. If I know the temperature, Q flux, I can calculate this temperature profile. And can I assume it's a constant surface temperature? I can assume this is 0, okay? But this one is, we know that, but it's not constant, it's changing slowly, okay?
Sir?
Yes, dear.
Is it temperature profile only from the center to the surface of the tube or throughout the tube?
It's symmetric. It's symmetric, therefore you change at the center R equals 0. At center
Okay.
R equals 0, therefore we can go up or down, but the symmetric is the same.
So it's from the center to the surface of the tube.
Okay, let me show you this figure here, sir. If I find the one here. Look at here. If I assume it is temperature profile, temperature at the profile is either maximum if we are dealing with heating, or we are dealing with the cooling, okay? In the case of cooling, the temperature at the surface is lowest, at the center is highest. If I'm doing the heating, the temperature at the surface is highest up here. Therefore, this becomes like this, becomes in the opposite direction.
Okay.
But since we are assuming R is equal to 0 here, and R change, therefore it becomes symmetric. The temperature this side is exactly the temperature of this side.
Yes.
Okay. For now, we end up with all of this calculation. We end up to do that one, and we find that now we have an expression. We can calculate the surface temperature, mean temperature, and then knowing this equation is equal to this, Q, how much energy provided to the surface, is equal this Ts minus Tm, and I calculate the average mean temperature. Average mean temperature, replace it here by equating these two equations here, from taking Ts from here and placing here and putting Q dot and so on. I can calculate my H, and my H gave me is 4.636. Okay, if I define the Nusselt number for circular tube, laminar, constant heat flux, my Nusselt number is always constant. Okay, let me go back one more time and explain it to you. Therefore, we find the velocity profile and you have no problem. Okay, let me go back again to just explain to you one more time. You mentioned we're trying to find the value of H. Therefore, we write this force balance equation to find the velocity profile. I'm sure by now you have to know this equation. I found an equation that gave me the velocity as a function of R. If you plot this one, you will see it's hyperbolic. It means it's the shape that you have. And then we wrote a simple energy balance equation for the control volume again. Again, control volume has a thickness of dr and length of dx. Fluid is passing through here, this control volume, the temperature Tx, and coming out at Tx plus dx. And also, we mentioned there is a temperature variation in the R direction. For some heat flux from here by conduction, pass and conduction. But we simply write this expression that we have. Therefore, here, by motion of the fluid, and this is by conduction. And we replace this one, m, because mass going to here, we're trying to calculate how much it is density, time velocity, time cross-section area of this one. Cross-section area is R times dr here. Okay, that's the area of this cross-section area, this part that we have here, this thickness. We put them in this equation together. Here, this change the temperature, conduction, and then we simplify here. This becomes dt over dx. This becomes dq over dr. And by replacing the qr here, this conduction that we have, this is Fourier equation for cylindrical coordinate, become a times k times a times dt over dx. And here we simplify, this becomes this term. Okay. Therefore, we place them here to calculate here. And then we simplify this equation, become here. Therefore, I place this term here. This term here is equal here. Cut them and end up with this one. This is energy by fluid motion. This is conduction in R direction. Okay. Now, if you look at here, I have one T variable and U is variable. I have already an expression that gave me the velocity profile. I can put it in this equation right here, and this equation becomes only a function of R. Therefore, here, okay? Therefore, this represents by fluid motion, and here represent by conduction. Therefore, if I put it there for the case, remember that ladies and gentlemen, we talked about constant heat flux, and we proved it before. This slope and this slope are the same, okay? We mentioned this slope dt over dx, this one, surface temperature and fluid motion are the same. This is something that we're going to use this expression. Therefore, I have this equation that I have it right here. This is my heat flux, and this I put them together. I solve this differential equation, taking two derivatives, one here. I have two constants. But I have also two boundary conditions. I know at the center of the pipe, because of the symmetric, dt over dr is equal to 0. And also I know the temperature at a point, okay? Therefore, this I place at the boundary condition. This is equal to half here, R because of symmetric, and we assume the temperature at the surface Ts, any variable, okay? If I put them here, I get this expression right here. Okay? Therefore, if I know the temperature at the surface, if I know it Q flux, I get here. But that's not my problem. My problem is trying to calculate H. calculate the H, I will go back and I use the concept I defined earlier. I said energy transfer by convection is equal energy transfer by conduction at the boundary layer, okay? Because we assumed in the boundary layer, heat transfer is by conduction. Therefore, by putting that, I can get this Tm. I can find the average T velocity. Socket machine. Therefore, I can find the average velocity, put in that equation that I have here, right here. This is known. This is Ts minus Tm. And I can replace it here, IQX, and I can find here. I can find my H value. My H is unknown. Therefore, I can find H value is equal, based on this equation, is equal 4.36. K is the same K here, and R is equal to D, okay? But if I put this one, convert this expression that I have to Nusselt number, I will find expression here, okay? This is the same as here. I put HD over K, I can find my Nusselt number, and here. That means, again, this is very important. After the fluid becomes fully developed, the entrance effect disappear. Okay, the entrance effect disappear when it's fully developed. The Nusselt number remain constant. The Nusselt number in case of constant heat flux. Constant heat flux. Remember, constant heat flux. The Nusselt number is 4.36. Okay. Therefore, please read it and try to understand. For fully developed laminar flow in a pipe, circular pipe, subject with constant heat flux, the Nusselt number is a constant. There is no dependence on the Reynolds number or Prandtl number. As long as the laminar, and doesn't matter the values here, it could be gas, it could be fluid. For any case, because when we solved all of this equation, we did not make any assumption if it's gas or fluid. Therefore, this is independent of Reynolds number and Prandtl number. Therefore, this is the main constant. Any question? Any question? Okay. Let me go a little faster. When I go to the case of constant surface temperature, the conductivity of the K is for use for Nusselt number is evaluated at bulk mean temperature. And the expression that we have, again, this is the 4.36. It was for constant flux. When it comes constant surface temperature, the Nusselt number becomes 366. Okay, therefore, keep in mind, you have to, when you use the value, is depend on your boundary condition. If it's constant heat flux or constant temperature. Therefore, for our final number, when it's non-circular, we have a table, and that table give you the value. Okay, this was for the pipe. This value and that value what was for the pipe, but we have a table, and that given as based on hydraulic diameter. Hydraulic diameter. Therefore, for any geometry that you have, is rectangular, square, and so on. First, you define your hydraulic diameter, and then based on that hydraulic diameter, you calculate your Reynolds number, and then you go to table 8.1. Similar to table 7.1, you have dependent geometry. If it's circle, if it's rectangular, if it's ellipse, if it's this one, all of them depend on your so. Okay. Therefore, this specify the boundary conditions. If it's constant temperature or constant heat flux, and they again depend in the case that you have rectangular here or this down, you define the ratio between A to B. This is A to B, and in this case, it's alpha. Okay. Depend on this angle that you have, your fluid, your heat transfer coefficient will change, and these are the values that you can calculate. Okay. Therefore, this is your Nusselt number. These are Nusselt number that you have different case. Okay. When you're dealing with Reynolds number with the pressure drop, these are your F value. Okay. You have seen this one before, 64 Reynolds number. Okay. Therefore, now you have it a graph or a figure that they gave you the Nusselt number for laminar flow fully developed. But please pay attention. Here it's mentioned it has to be, this does not work for entrance part. The velocity and temperature profile has to be fully developed. If it's fully developed, you calculate dr, dh, and then you calculate your Reynolds number, and you come here and you find what is the value of your Nusselt number, okay? And then you go back and you calculate your H value. I will stop here. Any question? Any question, ladies and gentlemen?
Sorry, where is the DH in the table?
DH is not in the table. DH is in the equation that uses Reynolds number.
If you said once we find that, we can find the Nusselt number in the table.
Yeah.
How do we do that?
Yeah, you calculate your Reynolds number.
Yes.
If it's laminar, you come to this table, right?
Yes.
And then you have boundary condition, constant temperature or constant heat flux. Then use one of these two in the case of pipe. If it's different geometry, you have to also pay attention to the dimension that you have A and B. But the only, this one you calculate in to find out if it's laminar or not. When it's laminar, you come here, and then you have based on the boundary condition.
Okay.
Any question, ladies and gentlemen? Okay, please start to read now. You have no excuse. The project is finished. And then we start to do more problem from previous chapter. I know there is one problem left from chapter 7. We will try to do it next lecture, but please read chapter 7, chapter 8. And we try to do one problem also from chapter 8, at least you see the application.
Sir?
Anyway, yes, sir.
For the midterm, which chapters are going to be included? Up to which chapter?
Give me a number.
No, I'm not doing
come on,
that.
give me a number.
No.
Okay,
I'm not taking that responsibility.
Oh, you said chapter 6. Okay, until the end of chapter 6.
Well, I didn't say anything, but okay.
Okay. Now, because the idea here, I just would like to make sure that you have enough practice, because not the quantity. The question here, I want to make sure that at least the first 5 chapter, at least you have a complete understanding, because
Okay.
I believe this week you are going to solve some problem for chapter 7. Therefore, I would like to have enough time to go through it, understand. Meanwhile, I will spend more time chapter 7 and 8, that at least we can catch up the whole subject we covered so far. It's good. Therefore, you can bring 2 formula sheet. 2, 2, 2. Okay, 1, 2, and you can write both sides. It means you have 4 page.
Okay.
Anyone? Okay. Any other question? I'm here. Lecture is finished. If any question that you have, please do ask me.
Sir, just about the equation sheet.
Yes.
Will we have to include tables in that as well, or will you provide any tables?
No table, no figure, nothing. Those are just the loose equation here and there. If whatever is in table and if it's needed, I will provide you. Okay.
Okay, thank you.
That's easy for me because I can make a photocopy and add it. But the other equation, I do not know which one you needed. Okay. Therefore,
okay, thanks.
Only write those equations that you can see spread all over the textbook.
Thank you, sir.
Thank you. All the best.